Hi, welcome to the session. Today we will explore the core architecture of Hadoop, Yarn, MapReduce, and Zookeeper. Please feel free to stretch any time. Here you come. Here's our learning curriculum for our session. I divided this workshop into 6 topics: Hadoop distributed file systems, big data NoSQL database, Kafka, Spark, and Libby, and Delta Lake. Some people might wonder why I didn't start with Hadoop. Well, Hadoop became a folktale a while ago, and Spark has been dominating the market since late 2017. When I talk to my best friend at Google Cloud, he always loved to say Hadoop is dead. But I always tell him that I wouldn't say that just yet, since Spark is running on Hadoop's paradigm of distributed computing. I'd say Hadoop is a grandfather of Spark who's living together. So back to our slide. I chose multiple subtopics per section, and I grouped the topics that are relevant to each other. I may add or change subtopics, but I hope you feel motivated to learn about the most cutting edge organizations are dealing with big data these days. Today, we're going to deep dive into the underlying framework of Hadoop that are the foundation of how Spark became what it is. My subtopics for today's sessions are Yarn and Zookeeper, but I will also add HDFS and Hadoop file formats as bonus. After Zookeeper chapter, I'll have a code demo to show you. Let's go over some important vocabularies that we need to know before deep diving. Distributed file system is a file system that manages underlying storage across network. Simply put, since they are network-based, all the complications of network programming kick in. This makes distributed file systems more complex than regular disk file systems. Biggest challenge here is making the file system fault tolerant with a zero data loss. Hadoop is a platform that runs on parallel processing framework in a distributed file system. When I say you can store any types of data without placing any constraints, it means that Hadoop is a schema on read. You don't have to expose schema before the data is loaded. HDFS. Think of block file system or disk block, but it is much bigger. The HDFS default block size is 128 megabytes compared to the file system block, which is few kilobytes, or disk block is about 512 bytes. Just like the file system blocks, they are broken down to block size chunks, which are stored as independent units. One HDFS block containing a file size of 1 megabyte only uses 1 megabyte of disk space, not the entire HDFS block size of 128 megabytes. Name node keeps a snapshot of the entire directory structure of the file system. We call that metadata. And that keeps track of where they are located in the cluster. Name node can list the blocks and its location for any files within HDFS. We call name node as the master or head node. So it is a single point of failure in Hadoop cluster. Data node stores all data in HDFS. We call them as slaves, since its sole duties are to let name node know they are still alive along with the list of blocks that are stored in them. It is not fault tolerant. If it goes down, and the master replicates contents in the data node to another server. You may wonder, how do name node replicate the data in data node if the data node goes down? I'll talk more about replication logic in my later slide. Yarn became one of the sub-projects within Apache Software Foundation in 2012 and became one of the key features in Hadoop 2.0. It was GA in later 2013. GA means general availability, which is ready for mass production. It provides APIs for requesting and working with cluster resources, but they're not used directly by the user code. What I mean by this is users need to write to high-level APIs that are built on Yarn and make the resource handling details hidden from users. There are three major components in Yarn. Resource Manager is responsible for scheduling application jobs and monitoring resources in the cluster. Node Manager is responsible for launching and monitoring containers and their resources usage, like CPU, memory, disks, and report back to the resource manager. Container executes application-specific program with a specific resource allocated to them. Finally, MapReduce is distributed data processing algorithm introduced by Google and is very effective in processing huge amount of data in parallel in cluster environment. Then you may ask, what is the difference between Spark and MR, which is MapReduce? MapReduce uses persistent storage, whereas Spark uses RDD in memory. Okay, then let's get to the gut of it. Hadoop architecture. So you have two siblings in Hadoop, HDFS and Yarn. For HDFS, I have a dedicated slide for it, so I will deeper dive in there. For the Hadoop architecture, you got name node that manages and schedules jobs, and data node that writes data in block in storage. Resource manager, who is responsible for job scheduling. Node manager, who manages pool of resources. There's edit log that keeps track of name node states and synchronizes edits, which is equivalent to transactions of primary name node with failover name node of the HA purposes. HA means high availability. When you think about the flow of Hadoop, it starts by app client submitting Yarn application to Resource Manager, and then Node Manager starts and launches application processes in a container. While application is running in a container, the app master requests more resources from Resource Manager. Under Resource Manager, there is Yarn scheduler that allocates resources to applications with some defined policies. There are three scheduler options: FIFO, capacity, and fair schedulers. Very briefly, the capacity and fair schedulers can start jobs in different queues in parallel or asynchronous job execution. These schedulers options are often used for shared clusters, which applies to most of the clusters. Then there's Application Manager. It manages the execution of applications. It asks for container from the resource manager and execute specific programs in the container. Container executes application-specific processes. App Master is a process that runs computation inside of the container and return the result to the client. As for the edit logs and journal node, when the name node fails, there is a snapshot image of the file system's metadata called fsimage. But since it is a point-in-time snapshot, all the operations are recorded in edit logs. The name node restores them by loading the fsimage, then replaying all the operations in the edit log to read the most recent state of the file system.